Hey friends, welcome to our last unit of calculus, and an exciting unit of calculus because we get to look at things in a whole different way, really. We've spent our whole course really understanding what a derivative is and getting a function and figuring out the derivative and looking at all the applications around that. Now we start going backwards. Okay, so now we pose the question, what if you have the derivative and you want to figure out what the original function is? Now, some of you are sitting there saying, why would we do that? Well, my first answer is because it's fun. But my second answer is there's a lot of real world context where we are actually dealing with the derivative and we don't know what the original function is. So we can backtrack and get the original function, okay? There's also a huge concept in calculus around getting the area under a curve. I don't know if you remember the very first day we were together, we did that introduction to calculus and we talked about trying to find the area of the curve. And we talked about saying, you know, the area of the curve could be like an infinite amount of rectangles added together. We're going to get into that now here as well. Okay, today's lesson is rather long, as is, you know, most introductory lessons to a new unit. There's a lot of ground we have to cover, so make sure you're using this video well. Stop, pause, rewind, do it again. Okay. The more you can go through this and the more you can hear the repetition, the better you're going to feel about things. Okay, so that was my little lecture to start. Differential calculus is what we've been doing so far all year. Differential calculus involved finding the y value of a function at a particular point by taking the limit of the function as it approached a particular x value. This led us to two different points. Point one is we were able to determine a general expression for the slopes of a particular function. That was called the derivative of the function. Okay, all of that should sound at least vaguely familiar at this stage of your life. Number two, the slope of a function at a particular point, and the way we would get the slope at a particular point is we would substitute into the general expression, i.e. we would evaluate the derivative. Okay. Integral calculus is the reverse of differential calculus. So it's going the other way, okay? In many cases, we know the derivative of the function and we need to determine the original function. That's called the antiderivative, okay? The antiderivative refers to the original function when given the derivative. Okay, this is an inverse operation and is called antidifferentiation or integration, okay? Anti-differentiation or integration. See how smart you guys are going to be with all your new vocabulary? If f of x is 10x, if f of x equals 10x is the derivative of some function, big F of x, determine big F of x and sketch it. Well, just use some logic. Think about what the original equation would have to be so that when I take the derivative, I get 10x. Well, most of you are going to think right away, I would need an x squared, because when I go to take the derivative of x squared, that 2 comes to the front, right? And then it gets multiplied by whatever's originally there. So now you're going to ask yourself, okay, if that 2 has to come to the front to get multiplied by something and get 10, what was the initial coefficient on that x squared? It had to have been a 5. So I would want you in your head, pretty comfortable right now, even without us doing much, to say it's going to have to be 5x squared. The derivative of 5x squared would be 10x, okay? So can you think of a function, f of x, so that when you take the derivative, it will be 10x? Well, sure we can. It's 5x squared. Now, here's the other thing to talk about, though. Why couldn't it have been 5x squared plus 9? When I take the derivative of 5x squared plus 9, the derivative of 9 is 0, so I'm still left with 10x. True? Or it could have been 5x squared minus 33, or it could have been 5x squared plus 1,123,456,789. Okay? And so I could have any sort of constant number that I want there. Okay? And so what we often do is we say it would be 5x squared plus c, where c is the constant of integration. Okay, so we say that the general solution is f of x equals 5x squared plus c. C is called the constant of integration. Because we do not know c, the antiderivative is sometimes called the indefinite integral. Now, there will be opportunities along the road where we actually do figure out c in a particular context, okay? But when we're just writing c, that is then sorry, can't get that out. Then the antiderivative is called the indefinite integral, okay? All right, so let's look at how we would approach each of the kind of derivative rules that we talked about. We're going to look at them and say, how would we have approached them the other way? Okay, so for constants, if I just had a number, that's what k is there, f of x equals k. So if it was just f of x equals 3, the antiderivative of that would have to have been 3x, right? Because when I take the derivative of 3x, I just get 3. So you're asking yourself here, how do I go backwards? Okay, for the power rule, if f of x, little f of x was kx to the n, well, you know that n has to go up a degree, so that's why it says n plus 1, right? And then essentially, you're going to have to divide whatever k is by that new exponent that you're doing, because if you go to take the derivative, that new exponent comes to the front and gets multiplied. So when you're going backwards, by dividing, you are ensuring that when the first guy comes up to the front and multiplies, they'll divide each other out, right? Now, some of you are sitting there with deer in the headlights right now because I can just tell. So I want to just have that conversation one more time. The reason we're dividing, okay? If this ends up being the derivative, if this ends up being the original function, and I want to go take the derivative of this, this comes to the front and gets multiplied. So I'll have n plus 1 divided by n plus 1. That would divide out my n plus 1s, and I'd be left with k, which is what I want to be left with. Okay? Okay. For e, we know the derivative of e to the x is e to the x. So just dealing with all the coefficients that I could have on here, if f of x was a e to the kx, what would happen there is my original function, my antiderivative, would have to have been a over k, e to the kx. Because remember, when we're taking the derivative of something that looks like this, sorry, I'm just getting my ink back on, something that looks like this, the derivative of that would be that times the derivative of the inside function. Well, the inside function would be kx, and the derivative of kx would be k, and that would divide out the k's that I need to divide out. Okay? You're gonna get this, okay? New things always seem a little overwhelming at first. This is gonna go really smooth. You just need to give yourself some time, okay? All right. For natural logs, if the derivative was 1 over x, then the original would have been ln of the absolute value of x, because we know that the derivative of ln x is 1 over x. Okay, again, I'm ignoring the plus c here, but all of them will say plus c because all of them could have some sort of a constant on them. Okay, make sure when you're telling me the antiderivative that you do say plus c there. Okay. Okay, now for trig. We know the derivative of sine is cos. So if my derivative is cos, then I would say the antiderivative would be sine x plus c. We know the derivative of cos is negative sine. So if I'm at sine and I need to take the antiderivative of that, that would end up being negative cos x. Okay, then if I throw in multiple angles, the same sorts of things happen. Okay, so what happens is whatever the multiple angle is, that's going to have to get divided by the coefficient that's in front. Because again, I know I've said this already, but I really want to try and help you understand what we're doing. If I was to take the derivative of what I just boxed there, the derivative of that would be cos of that times the derivative of the inside function. And the inside function derivative would be k, and that would divide out my k's and leave me back with just the a in front of cos. Okay. Likewise, for a times sine k of x, it would be negative a over k cos of k of x plus c. Sorry, cos of kx, not k of x. Okay, awesome, awesome. Okay, so let's try a few examples. So if f of x is 2x cubed plus 3, so that's little f of x. Little f of x will refer to the derivative. Big f of x refers to the original function or the antiderivative, okay? So determine the antiderivative. Now, here's what I want you to think through. This guy in the original function is going to have to be a 4. Okay, so if that guy is going to have to be a 4, I'm going to have to divide him by 4. This guy is going to have to be a 2. Because when I go to take the derivative, I drop a degree, right? Okay, and if that's going to be a 2, I'm going to have to take what's a coefficient of 1 right now and divide that by 2. Okay, so essentially, the original function would have to have looked like 1 over 2x to the 4 plus 1 over 2x squared plus c. Okay, now in my notes here, I made things, you may look at this and say, well, this looks way more complicated than what you just said, but I'm just trying to get you to see the formula. I'm not requiring you to do this, but if you're looking for that formula, what we did was we raised the original by 1 degree, and then I divided whatever the n value was, I divided it by in the coefficient. Okay, and then same thing here. But what you get is exactly what I said, 1/2 x to the 4 plus 1/2 x squared plus c. Okay, now could you check your answer? Sure you could. You could take the derivative. So if I took the derivative of this, the 4 comes to the front, 4 times 1/2 is 2, and this drops a degree, so that would be 2x cubed. Check. Taking the derivative of this, the 2 comes to the front, 2 times 1/2 is 1, this would drop a degree, and so that would leave me with x, check. Okay, and then the derivative of c would be 0, so everything works. Okay. All right, I'm just going to take my ink off there, and we'll go to the next example. So, again, it gets a little bit more complicated just because it's longer, but it's the same process. I'm going to go term by term. So this -6, I have to raise that a degree so that when I take the derivative and lower it a degree, I get back to -6, right? So that -6 is going to be raised to -5. Now, that means I'm going to take my -2 over 3, and I'm going to divide that by -5. Okay. Well, -2 over 3 divided by -5 is the same as -2 over 3 times -1 over 5. So that would be what? 2 over 15. So my coefficient there is going to be 2 over 15, x to the -5. Here, I want you to notice that 1 over x, that's going to be ln absolute value of x. Okay, ln absolute value of x. Here, this is going to be raised to an 8, so then this will end up being 6 over 8, which will be reduced to 3 over 4, and then this will be 3x, okay? Now, I'm trying to get my ink off and talk to you at the same time, and I'm a guy and we don't multitask well. Okay, so this is what I just said, and then when I cleaned it all up, this is what I got. Okay, again, I don't necessarily need to see that first line. I'm doing that first line for your benefit, just in case you get lost in the video as to, well, what sort of a process was he using, okay? I did that one probably 3 times as quick as I did the first one. And I didn't do that to stress you out. I'm hoping that you're clicking into kind of the process that we're doing here, okay? Okay, could we check? Sure we can. If I brought this guy, if I took the derivative of this guy, the -5 would come to the front. That would end up being -2 over 3, and this would drop a degree to -6. Check. The derivative of ln x is 1 over x. Check. For this guy, the 8 would come to the front. I would get 8 over 4, which is 2 times 3, which is 6, 6x to the 7, check. The derivative of 3x is 3, check. Everything works, okay? Okay, so try this guy. The derivative is cos of x. What's the original? What's the antiderivative? Well, what gives me, when I take the derivative, gives me cos of x, and that would be sine of x. So it would be sine x plus c. Okay, f of x will be sine x plus c. Could I check? Sure. The derivative of sine x is cos x. Done. Okay, so next one, if f of x is 2 over 3 sine x plus x squared plus 2 over x plus a half, determine the original function, determine the antiderivative. So I know that the antiderivative of sine x will be negative cos x. So this is going to end up being negative 2 over 3 cos x. This has to go up to 3. So this will end up being 1 over 3 x cubed. When I have a 1 over x, the antiderivative of that would be ln absolute value of x. So that would be 2 times ln absolute value of x, and then this will be 1/2 x. Okay, so I just treat each one almost like a separate question, and I know how to handle each one. Then I put it all together, and don't forget to add the c at the end. Okay, perfect. Okay. If f of x is 2 cos of 4x, then determine the original. Okay, so I know that the antiderivative of cos would be sine, but I'm going to have to end up dividing by that coefficient there. So I'll have 2 over 4. I have to divide by the coefficient on the multiple angle, not the coefficient on the whole thing, right? And so that'll end up being 1/2. And again, the reason I do that, remember when I go to take the derivative of this, the derivative of this would be 1/2 sine of 4x times the derivative of the inside function. The inside function is now 4x. The derivative of that is 4. So I end up with that 4 times 1/2, and that puts me back to the 2. Okay. And so yes, I just checked it. Okay. All right. F of x equals e to the 2x. If I want the antiderivative of that, again, I've got that inside function problem going on. So I'll have to essentially, the derivative of the antiderivative of e to the 2x would be e to the 2x, but then you have a 1/2 in front of that to account for when you go to take the derivative. So it'd be 1/2 e to the 2x plus c. And again, to check, the derivative of 1/2 e to the 2x would be 1/2 e to the 2x times the derivative of the inside function, which would be 2. And then that 1/2 times 2 puts me back to the 1 that I wanted. Okay. Okay, if f of x equals negative 4 over 5 sine 2x minus 3e to the negative 3x plus cos of negative 3x, determine f of x. So again, we're just going to take this step by step. The derivative of sine, the antiderivative of sine would be negative cos, but I'm also going to have to divide everything by 2 on the front here, okay? So if I divide by 2, that's going to end up being 2 over 5 here. And I don't know if you caught that or not, but I'm going to have 2 negatives there. I'm going to have the negative here, and then I'm going to have a negative cos. So that'll overall just end up being positive. For this guy, the antiderivative of that would be 3e to the negative 3x, but I'd have to take that negative 3 and divide it by this guy. So that's actually going to end up being positive 1. And then for this guy, it'll be negative 1/3 sine of negative 3x. Okay, again, for the same reason, the antiderivative of cos is sine, and then I have to divide the coefficient by the negative 3. Okay, so I have 2 over 5 cos of 2x, I have plus e to the negative 3x, and then I have negative 1/3 sine of negative 3x plus c. If I was to check it, again, the derivative of cos is negative sine, and then I'd have to multiply this by 2, and that would give me my negative 4. So that negative 4 over 5 sine 2x works out. Here, the derivative of e to the negative 3x is e to the negative 3x times the derivative of the inside function, which would be negative 3, and that works out. And then the derivative of sine of something is cos of something times the derivative of the inside function, which would be negative 3. And when I have that negative 1/3 times negative 3, I get my positive 1 coefficient there. And then the derivative of c would just be 0. Okay. All right. Let's try this one. If f of x is the root of x minus cubed root of x to the 4 plus 6th root of x to the 5 minus 6 over root x. Now, the first thing I'm going to do is just try and clean this up a little bit and represent it more in exponents than in roots. So I've got x to the half minus x to the 4 over 3 plus x to the 5 over 6 minus 6x to the negative a half. Okay, so really all of these are just powers, which means each one of them has to get raised a degree, and then that new exponent has to get divided by the coefficient in front. Okay, so 1/2 raised a degree would be 3 over 2. So I have to divide the front coefficient by 3 over 2. Well, that would be 2 over 3, right? 1 divided by 3 over 2 is 2 over 3. 4 over 3 raised a degree would be 7 over 3. So I'm dividing by 7 over 3. 1 divided by 7 over 3 would be 3 over 7, so that would be negative 3 over 7. 5 over 6 raised a degree is 11 over 6, right? I'm just adding 6 over 6 to that. So I'm dividing by 11 over 6, which would be 1 divided by 11 over 6 is 6 over 5. And then negative a half raised a degree would be positive a half. So I'm dividing negative 6 by positive a half, which would be negative 12. Okay. So I end up with, isn't this fun? I end up with 2 over 3, x to the 3 over 2, minus 3 over 7, x to the 7 over 3, plus 6 over 11, x to the 11 over 6, minus 12, x to the 1/2, plus c. Now, all I've done is I've gone back and put it into roots again, just because writing it as roots is usually kind of looks a little cleaner than having all those fractional exponents. Fractional exponents are actually hard to read, especially when you got a lot going on. So in that sense, writing it as roots would be better. We want the fractional exponents just so that we can handle the changing of degrees, okay? Okay. And then if I was to check it, well, let's just go back here to check it for a second. This would, the 3 over 2 would come to the front. 3 over 2 times 2 over 3 is 1. This would drop a degree, so that would become 1/2, so that works. The 7 over 3 comes to the front, I get negative 1. This would drop a degree, I'd end up with 4 over 3, that works. The 11 over 6 would come to the front, I get 1. When I multiply those together, the 11 over 6 would also drop a degree to 5 over 6, that works. The 1/2 would come to the front, negative 12 times a half is negative 6. This would drop a degree to negative a half, everything works. Okay. Okay, if f of x equals negative cos of x over 5 minus 2 sine 2x over 3, determine the antiderivative. So the derivative, the antiderivative of cos is sine, but then I have a 1 over 5x there, so I'd have to take my coefficient and divide by 1 over 5, which is the same as saying multiply by 5. So that's going to end up being negative 5 sine of x over 5. The antiderivative of sine is negative cos. But then I'd have to take my negative 2 and divide by that 2 over 3. So negative 2 divided by 2 over 3 is the same as negative 2 times 3 over 2. So that'd give me negative 3. But also take note that the antiderivative of sine is negative cos, so my two negatives will actually make a positive there. Okay, so I end up with a negative 5 sine of x over 5 plus 3 cosine of 2x over 3 plus c. Okay. check it? Sure. The derivative of sine is cos. And then I have to take the derivative of the inside function, which is 1/5. 1/5 times 5 gives me that -1 that's there. The derivative of cos is negative sine. Then I have to take the derivative of the inside function, which is 2/3. 3 times 2/3 would give me back to that -2. Okay? Okay, so if f of x equals whatever, 9,999,999 minus 9/x cubed plus the root of x cubed over the 5th root of x, determine the antiderivative. Well, we're going to clean this up a little bit. I want to write this with exponents first. So my something over x cubed becomes something times x to the -3. This becomes x to the 3/2 over x to the 1/5. Now, when subtracting, when dividing powers of the same base, I subtract the exponents. I'm thinking too far ahead in my conversation. I need a common denominator there, so common denominator would be 10. That would be what? 15/10 minus 2/10, so that'd be 13/10. Okay. So again, I've just cleaned all this up. So now I haven't taken the antiderivative yet. I'm just cleaning up the derivative. So now this will be 9,999,999x. This has to go up to -2, which means this will be -9 divided by -2, which will be positive 9/2. This would have to go up to 23/10. I just added 10/10 to that, which means I have to take my original coefficient of 1 and divide by 23/10, which would be 10/23. Okay, plus c. Okay, so now I'll put it back into like the roots and the non-negative exponents. So this guy here is going to be 9/2x squared. And then this guy here will be the 10th root of x to the 23. Okay, so that would be considered the cleaned up version of that. And if I wanted to check, sure I can. The derivative of this guy would give me just the 9,999,999,999. I wasn't paying attention, but you get it. This would end up being x to the -2. It would, the -2 would come to the front. That would give me -9, and it would drop a degree to -3, and that's exactly what this is. Okay. The 23/10 would come to the front. I'd get a 1. I drop this a degree to 13/10, and that works. Okay. Okay, cool. Now, the next two are challenges that lead into a concept of substitution that we'll look at tomorrow. But how I want you to handle them today, because we are still doing them today, how I want you to handle them today is just with a little bit of educated hypothesizing, shall we say, okay? Okay, if f of x equals 3x squared over x cubed plus 1, and I want to determine the antiderivative. Well, how am I going to do that? What I want you to look at, is that x cubed plus 1 for a second, okay? Because I know that the derivative of x cubed plus 1 would give me 3x squared. So if I'm thinking about just that x cubed plus 1, the 3x squared is going to show up just by me looking at the x cubed plus 1. Do you know what I mean? So right now, my answer is x cubed plus 1 to the -1, essentially, right? And so anytime I have 1 over something, that's the ln. So I'm going to look at this as the ln of x cubed plus 1 plus c. Now, did it work? Let's try it. The derivative of ln of x cubed plus 1 would be 1 over x cubed plus 1 times the derivative of the inside function, which would be times 3x squared. And that would indeed give me 3x squared over x cubed plus 1. Okay. Okay, so if f of x equals x cubed minus 2 to the 4 times x squared, determine the antiderivative. So here's the kind of conversation I want you to have in your head. I need to build in equations that when I take the derivative, I get that, okay? Well, I see right away x cubed minus 2 to the 5, okay? Because if I took x cubed minus 2 to the 5 and I brought that to the front, this would be 5 times x cubed minus 2 to the 4 times the derivative of the inside function. Well, the inside function would be times 3x squared. True? Okay, so that would give me 15 x cubed minus 2 to the 4 times x squared, which is not what I want, because I don't want a 15 there, right? Which means I need to introduce a coefficient of 1 over 15 in order for this to work. If my original guy was 1 over 15, then when I do the derivative, I have 1 over 15, 1 over 15, and that would give me exactly what I want, okay? And so I would be looking at 1 over 15, x cubed minus 2 all to the 5, plus c. Okay, now tomorrow, this was kind of a, let's just puzzle it and guess and check our way through with some logical thought. Tomorrow we're going to talk about a method of U substitution. We did something similar to that previous in the course, and whoops, that'll help you out. My marker just dropped out of my hand and slammed on my keyboard. That was the noise you just heard. Okay, now in your book you go right to a practice section because that finishes 6.1, but I'm happy to say that this lesson is actually a combination of 6.1 and 6.2 because 6.2 is really, really short. So the practice section is for you to do later. Skip over to 6.2, which, depending on the year you watch this video, is currently on page 318. Okay, so the examples we've done so far are called general solutions because the constant c is unknown. And remember, I said in 6.1 that these are sometimes called indefinite integrals. With additional information, we can find the specific solution by determining the value of c. Okay, so it's not too much complicated than what we've already done, I promise. So here, the derivative is 3x squared minus 7, and we want to determine f of x when f of negative 1 is 4. Okay, so the first thing we're going to do, just like we were doing, is we got to figure out the antiderivative. Well, this guy here is going to have to go up to 3, which means I have to divide this by 3. So that's going to be x cubed minus 7x plus c, right? I have to add an x onto that guy. So big f of x will be x cubed minus 7x plus c. Piece of cake. Now I have an x value and a y value. I'm going to plug that in and actually figure out c. Okay, so my y value is 4, my x value is negative 1. I get negative 1 cubed plus 7. Bring everything over to solve for c, and I get c equals negative 2. Okay, so when x is neg 1, the specific original equation would be f of x equals x cubed minus 7x minus 2. Okay, all right, let's try another one, and then we're going to get into an application of this. So if little f of x is 4x to the 5 minus 3x squared plus 2x minus 1, determine big f of x when its graph passes through the point 1, neg 1. Okay, so I have to take the antiderivative. This is going to move up to a 6. So 4 over 6 becomes 2 over 3. This is going to move up to a 3. Negative 3 over 3 would become negative 1. This is going to move up to a 1. 2 over 1 is 2. Sorry. This is going to move up to a 2. This is already a 1, and then 2 over 2 is 1. And then this will be negative 1x and plus c. Okay, so just to make sure you're all with me, 2 over 3x to the 6 minus x cubed plus x squared minus x plus c. Okay, now I know I have the point 1, neg 1, so I'm going to go plug in 1 for x and negative 1 for y and solve for c. Okay, when I do that, I end up with c being negative 2 over 3. So my conclusion is at x equals 1, the specific equation that this would work for is f of x equals 2 over 3 x to the 6 minus x cubed plus x squared minus x minus 2 over 3. Okay? Okay, so now we're going to take this just a teeny weeny step further and look at it from the purpose of an application question in motion problems. So this can be extended to motion problems. The antiderivative of acceleration is velocity, and the antiderivative of velocity is displacement. Those sentences should sound familiar to you because we've said them the other way before, right? We've said that the derivative of displacement is velocity, and the derivative of velocity is acceleration. So it would make sense that I can now go backwards. The antiderivative of acceleration will become velocity, and the antiderivative of velocity will become displacement. Okay? If the object is being thrown upwards, the acceleration is negative, and the velocity is positive. If the object is being thrown downwards, the acceleration is negative, and the velocity is negative. Okay? So whether I'm throwing upwards or downwards, acceleration is going to be negative. But then when I'm going upwards, velocity is positive. And when I'm going downwards, velocity is negative. Okay. An object starting from rest moves in a line with a velocity of v of t equals 8t minus 2t squared. How far does the object move? So I've asked you how far, that's a distance, that's displacement. Okay, how far does the object move in the first second? So I've given you a time value of 1, but I've given you the wrong equation. I've given you the velocity. I don't want to know the velocity at 1 second. I want to know how far it's moved, how far it's been displaced at 1 second. So I have to take my v of t and I have to find the antiderivative in order to switch this to a d of t equation. Okay, so 8t, the t has to become squared. So that'll end up being 4t squared. This 2 has to become a 3, so that'll be negative 2 over 3 t to the 3, and then plus c. So I need to think about my c value. But what do I know? I know that at time 0, my displacement is 0, okay? Because I started from rest. So if at time 0, my displacement has to be 0, then c has to be 0, because this would be 0 minus 0. I need this to be 0 as well in order to keep it at 0. Okay, so my equation becomes d of t equals 4t squared minus 2 over 3 t cubed. Okay, now I plug in 1, and when I plug in 1, I get 10 over 3 meters. So the object has traveled, the object has traveled 10 over 3 meters, okay? All right, last question for today. I know you guys are probably at this stage saying, oh, yay. Okay, a stone is tossed downward with a velocity of 4 meters per second from a bridge 100 meters above a river. How long will it take the stone to hit the water? So how long will it take the stone to hit the water? I'm actually looking for that x-intercept of the displacement function, right? But the only thing we've given you is the acceleration. The acceleration is negative 9.81 meters per second squared. So I have to work my way from acceleration up to displacement, okay? So the first thing I need to do is go from acceleration to velocity, which is taking the antiderivative. So my initial condition is at time 0, the velocity is negative 4, because it says a stone is tossed downward with a velocity of 4 meters per second. Okay, so my acceleration is negative 9.81. The antiderivative of that will be v of t, and that'll be negative 9.81x. Okay, so t in this context, so negative 9.81 t plus c. So now what I'm going to do is I'm going to plug in my initial condition so I can solve for c. My initial condition is t is 0 while the velocity is negative 4, which means c is negative 4. Okay, so now I have a velocity equation of negative 9.81 t minus 4. Perfect. Now I need to go and take the antiderivative of that so I can get to the displacement equation. Okay, so this is going to become a 2, right? So this becomes negative 9.81 divided by 2. This will be negative 4x, and then I'll have to add the c to that. Okay, so now I need an initial condition to plug into this in order to solve for t. So what pieces of the question have I not used yet? It was from a bridge 100 meters above a river. So at time 0, I'm 100 meters in height. Okay, so that means I can plug 100 in for my d of t and 0 in for my t and solve for c. And that gives me c equals 100. So my displacement equation for this context becomes d of t equals negative 9.81 over 2 t squared minus 4t plus 100. That's the one now that I need to figure out the t-intercept essentially. And that's when the stone is going to hit the water. Okay. Given this quadratic that I'm looking at, I'm not going to try and factor this because I've got this wonky coefficient in the front. So I'm going to go straight to the quadratic formula. Okay, setting it equal to 0 and solving. So my b value is negative 4. My a value is negative 9.81 over 2, which I just wrote here as negative 4.905. And my c value is 100. Okay, when I simplify that out, I'll get 2 different answers. One will be positive, one will be negative. I don't care about the negative one. I only care about the positive one on this one. So that was 4.13 seconds. Okay, so the stone will hit the water at 4.13 seconds. Regardless of how you feel about this first lesson, that's kind of cool. That's kind of cool that I can take those initial conditions and build my way into an equation to solve, okay? If you don't see its coolness factor right now, you will after you do a bunch of homework, okay? So speaking of homework, here's yours. Take your time. Remember, it's 6.1 and 6.2, so there's lots to look at here. And make sure you're connecting with me if you have any questions, okay? Good job, guys. Take care.